I would like to start talking about a problem that we actually don't have. Right now, we're not going to have to pack our bags back from the MIP workshop, unfortunately. But that does remind me of a problem that we do have in machine learning, which is to get a good accuracy in a particular task. Sometimes you have to train very large models, and these models may not be easy to fit in machines that we use on the day-to-day, so it's hard to embed them. And what I'm going to talk to you today is about how can we use MIP to make a neural network smaller by compressing it, while not affecting its accuracy, while not affecting in any way how this neural network behaves. And this is joint work with Abhinav Kumar and Shri Kumar Ramaligan. Now, I used to be a metristics guy. I'm not anymore, so I'm no longer keen on metaphors. So I don't actually want to think about the neural network as a metaphor for neurons in the brain. I would rather talk about it as a network that's going to model a function for us that maps from an input space X all the way to an output space Y. Now, one of the most commonly studied architecture is the feed-forward neural network, where you have a succession of layers that is going to transform the inputs all the way to an output. And within each one of these layers, we're going to use units that are commonly known as the rectified linear units. The way that each one of these units will work in a feed-forward neural network is that this unit is going to take as an input all the outputs from the previous layer and produce a single scalar as output, which is sent to all the neurons in the next layer. And this relationship between inputs and outputs, at least in the case of a rectified linear unit, is given by this expression in front of us. So HIL, which will be the output of the neuron, is going to be calculated as a maximum between 0 and an affine transformation of the inputs of the neural network. Now, when we train a neural network, we don't exactly choose how big it's going to be. That's a hyperparameter. But what we can choose actually is what we can adapt as we're training the neural network is this matrix of weights for each layer of the neural network and this vector of biases for each layer of the neural network. By adjusting their values using some optimization techniques, we can train the neural network to perform better in certain tasks. Now, if you send some input through the neural network, for a trained neural network, and the output of a neuron is 0, which means that the term maximizing this expression is the first one, then in that case, it's actually convenient to think about the metaphor. That's a case where we could say, for example, that the neuron is inactive because the neuron is not transmitting any signal forward. Although the silence of the neuron is also telling us that there is something there there's something that's not, whatever is the input that the neuron received, something that doesn't make it react. Now, the second term is going to be the case where the output is positive. And if that's the case, we can say that the neuron is active. Now, these two concepts are going to be very important for us as we think about how we can make a neural network smaller. So the question that I'm interested here is exact compression. So I'm thinking about whether we can find a smaller neural network that models exactly the same function. In other words, for every X, the mapping to Y is going to be preserved, hopefully with fewer neurons, and even better if with fewer layers. Although whether we can get there or not, it's open for discussion. Now, if we want to make this problem slightly easier to solve, we can think about these inputs as coming from a bounded set, let's say capital X. And that's something that we may see very often in practice, because in different applications, we may have inputs that are relevant for that application and inputs that would be meaningless. And to talk about one classic example, here we have the MIP-lib of machine learning. In other words, the MNIST dataset. So the MNIST dataset is the most commonly used benchmark for training machine learning models because everyone knows about it and the size is kind of reasonable. So in this dataset, every sample consists of a 28 by 28 matrix, which corresponds to a handwritten digit. In each one of the cells of this 28 by 28 matrix, we have a value between 0 and 1, And the closer you are to one, the darker, the closer you are to a black pixel. And the closer you are to zero, the closer you are to a white pixel. And with the MNIST data set, our goal is to look at these handwritten digits and infer whether they represent a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Now for the MNIST, the inputs will be bounded between 0 and 1 for every one of these 784 variables. So it doesn't really matter for us what happens if, for example, one of the inputs is negative or one of the inputs is greater than 1, because that's never going to happen in practice. Now, compression in neural networks is not something new. There's an extensive literature on inexact compression, which I won't be able to cover here, but that's actually the point of inexact compression. You're never able to keep everything when you do it. So the motivation in inexact compression is that we want to embed neural networks in smaller devices, and this has been tried in many, many different ways. And for some time now, we know that this is justified. For example, about 8 years ago, which is like prehistory for neural networks at this point, it has been shown that there's a lot of redundancy between the parameters of a neural network. In other words, you can predict the value of some parameters of the neural network by just looking at other values. Now, more recently, we have seen a lot of movement as well. So for example, Sanjeev Arora and some co-authors, they have shown that you can get better generalization bounds if, for example, you approximate a neural network with a low rank matrix for the weights. Then there are some recent comprehensive surveys. For example, Blalock and others, they have observed that there's this trade-off between compression and accuracy in this benchmark of 57 different compression algorithms that they analyzed. And we know that sometimes, we're going to actually get a slightly better accuracy with a smaller neural network. That can happen, especially when you do things very well. But the problem with that is that this is overall accuracy. That doesn't speak about what happens for individual classes. So there was a study by Hooker, and by Hooker here, I mean Sarah Hooker from Google, not John Hooker from Carnegie Mellon, as you would expect at MIP, where she and her co-authors analyzed what happens with compressed neural networks. They realized that these neural networks can be less robust. You can have some loss of accuracy, and this can be disproportionately distributed across classes. So even if your neural network at the end is not worse in terms of overall performance, you may have this neural network may be performing better in situations where it had a good performance. And for test cases where it wasn't performing well before compression, it's going to perform even worse. Which means if you think, for example, about facial recognition systems that are being used nowadays, there is this common understanding that the systems work better with white male faces and a lot worse with black female faces. And that has lots of bad consequences. For example, arresting someone on the grounds of like a predictive model that actually doesn't predict very well. So it's important to avoid this having this disproportional impact in different classes when we're creating a model that's going to be used. Now, recently, we have seen a lot of work in this area of compression that's moving towards optimization algorithms. So yesterday, Shantanu asked about how opportunities for applying discrete optimization in machine learning, and this is one of those. There are lots of different formulations. People have tried SDPs, integer programming, and all sorts of other formulations. And the one example that I'm going to mention here, because it's a MIP formulation as well, is this paper from last year from El Arabi, Wolf, and Carvalho, where what they do is they use a MIP formulation to score the neurons of the neural network in terms of their relevance to the outcomes. And then they remove the ones that are least important. So it's still a form of inexact compression, but powered by mixed integer programming. Well, that's going to be our lossy description of the inexact compression. Now we're going to talk about exact compression. That's a relatively unexplored area. But if we talk about exact compression, we don't want to miss out on anything. And in fact, I promise you, I'm not going to miss any papers here. And I'm not going to need another slide. And I can even put a bullet point about what's the point of exact compression, which is we can avoid the side effects that we have discussed before. For example, disproportionately distributing this loss of accuracy across different classes and the issues with robustness. And also the other advantage of exact compression is that you don't have to retrain the neural network. Because if you just start removing things at random in the neural network, or even in some guided way, that might have some side effects that you may want to avoid, or at least make up for by retraining the neural network afterwards. So, so there's one paper which was accepted this year at ICLR about identifying symmetry in graph neural networks. And last year at the CPI-WAR, we had a previous paper on compressing small rectifier networks. And we're done. That's what you need to know about the exact compression of neural networks at this point in time. Now, as I mentioned before, the way that we're going to do this compression is by identifying active and inactive neurons in the neural network. And we're going to use the concept of stability as well. So we can say, for example, that a neuron is stably inactive if it never produces a positive output. So no matter what input X from that set capital X you send through the neural network, when that hits the neuron, whatever transformations happen along the way, we're always going to get a pre-activation output, which is that affine transformation before the max of 0 and it should be smaller than or equal to 0. So the output is always going to be 0. So when that happens, we say that the neuron is stably inactive. We're never going to see a positive outcome from it, at least for a valid input. Now, a neuron may also be stably active if it always produces a non-negative output. So let's say for any relevant input that we can think of, as we send it through the neural network, we're going to get a pre-activation output before the nonlinear function, the max of 0 and this value here, which is always going to be greater than or equal to 0. And as a consequence, the output of the neuron is going to be equal to the pre-activation output. So we're not really, we're never outputting a 0 unless the pre-activation output was also 0. In both of these cases, this is relevant for us because this absence of a nonlinearity, of a discontinuity in the output of the neuron, of each one of these neurons, is going to help us simplify the neural network without changing what this function is modeling. And the way that we're going to do this, as you may guess, is by using optimization. So we can solve this problem here. We can maximize the pre-activation output of a neuron, so, given the valid inputs of the neural network, to see if we're going to get a negative value or not. If we do get a value that's smaller than or equal to 0 when you're maximizing the pre-activation output, we know that the neuron is stably inactive. We have a proof of that, which comes from solving the problem to optimality. We can also minimize the same expression. If by minimizing the same expression, we get a value that's greater than or equal to 0, that means that the neuron is stably active. So no matter what we try, we're never going to get a pre-activation output which is negative. And we can formulate a MIP for mapping inputs to outputs of a trained neural network. So I'm not training the neural network here. What I'm actually doing is I have the trained neural network. I'm using this as an input, and I'm just trying to figure out what would be the inputs that would maximize or minimize the responses of each one of the neurons. And the way that we're going to map these inputs to outputs is through a formulation that has been discussed very extensively in recent years, including some MIP talks. So I'm not going to spend a lot of time in this slide. The only thing I want to say here is that we have this binary variable z, which denotes whether a particular neuron is active or not. And this is going to be key for us in what we're going to do next. And just to graphically explain what we're doing when we're doing this formulation between inputs and outputs of each one of the neurons when they are ReLU, is that we're associating a value of 0 to this binary variable whenever the output of the neuron is 0. And in that case, it's because the pre-activation output is negative or equal to 0. And conversely, we're going to set a value of 1 to this binary variable z whenever the output equals the pre-activation output, which is greater than or equal to 0. So basically, we have a piecewise linear function, 2 pieces, and by defining and by using this additional h bar variable that you're seeing here, we can actually have a tight convex relaxation of this function in terms of g and h. And so putting it all together, we have two optimization problems with the same constraints. And I'm telling you that if we can solve these two MIPs, we can tell whether a neuron is stably active or stably active or none of those. Now, if we were in person, I would expect someone to stand up now because this is preposterous. And if that would be you, I would like to see you saying that in the chat. If you think some of your friends will do that, just send it in the chat as well. And why is this preposterous? Solving 2 MLPs per neuron is not cheap. I just presented you a MIP formulation with big M's, and I'm talking about neural networks that grow very large. So this is definitely not going to run in a reasonable amount of time. So yeah, I mean, that's what we did for the first paper, but we didn't stop there. We did add some tricks to at least like make this scale a little more. So what we were doing was we were using negative upper bounds. We would stop whenever we identified a negative upper bound for the maximization problem or a positive lower bound for the minimization problem. And by doing that, this is the runtime that we had to identify all the stable neurons of these neural networks. 2 hidden layers of 25 neurons each, 30 seconds. If you talk about 2 hidden layers of 100 neurons each, that scales to 400 seconds. So this is definitely not neat. I mean, this is taking more than training these neural networks on a CPU of the corresponding size. But there are some insights that we can have on this compression problem that can help us achieve more compression. So the first one is that we're solving all these problems over the same feasible set, basically mapping inputs to outputs. And the second one is that it's easy to certify that a neuron is not stable. Basically, we just need 2 network inputs as the certificate. If you show me one input for which the neuron is active, another one for which the neuron is inactive, I don't have to solve I don't have to solve any optimization problem anymore. I only have to care about solving optimization problems to certify that the neuron is stable. And in fact, one network input may actually be used to certify multiple neurons at the same time. So with that in mind, we're thinking now about a new optimization problem where we're trying to find an input that certifies as many neurons of unknown status as possible. So we want to send an input for the neural network, and we want to determine for these mysterious neurons whether the pre-activation output can be greater than or equal to 0, and like for a set capital P of neurons that we have never seen active yet. And also we want to know whether some of these neurons have a pre-activation output at some point that's smaller than or equal to 0 for a set Q of neurons that we have never seen inactive yet. Now, putting this all together, now we can have a binary variable for whether we have seen a neuron being active, P, and inactive, Q. So we're basically trying to maximize the number of neurons that we're going to see in a new state. And if by trying to solve this optimization problem, we have an objective function value of 0, then we know that every neuron in P is stably inactive. We can't find any instance where this neuron is active. And every neuron in Q is stably active because we can never make it inactive. And if this value, whenever we try to solve this problem, we get a positive value for the objective function, that just means that we are reducing the size of the sets capital P and capital Q and repeating the process one more time. And in fact, we just have to solve this problem once because the only time we need to solve this problem to optimality is when we want to prove that certain neurons are stable, which is when we're going to get an objective function value of 0. So if we find any solution of positive value along the way, that tells us what neurons we're no longer interested in, and we can just fix those variables to be 0 from that point on, basically by adding a lazy cut callback in whatever MIP solver of your preference. And in fact, we can even relax these new binary variables because we can leverage the integrality of Z. So basically, we have that objective function maximizing sums of P and Q over mappings of inputs and outputs of all the neurons of the neural network. Now we're bounding P to be between 0 and Z, and we're bounding Q to be between 0 and 1 minus Z. And now there is another insight about the MIP formulation here, for the MIP formulation of neural networks in general that can be very helpful for us, which is, and this is from Fischetti and Joe, which is that finding feasible solutions for these MIP formulations is easy. I mean, we know that in general, finding a feasible solution for MIP is NP complete. That's why MIP optimization is NP hard. But if you have any valid input for the neural network, you're automatically, and you pass it through you can automatically infer the value of all the variables in the system that we're using to model inputs to outputs. That doesn't necessarily mean that it's easy to solve a verification problem or any optimization problem over a neural network, because you have those ugly big M's and nobody had any smarter idea about what to do with them. But it definitely helps if we can get some feasible solutions along the way. So, and there is one feasible solution that's definitely going to be helpful for us. Let's say that we have an input associated with solving the linear relaxation. That's not exactly a feasible solution yet, but the inputs, but the values for the variables of the inputs can be used to define a feasible MLP solution, as if we just look at the variables for the inputs of the neural network, pass them through the neural network, infer what is the actual value for the rest, fixing all the integrality constraints. That's going to give us a feasible MLP solution. And this is a solution that's somewhat guided by the objective function, even though the relaxation is not that strong. And we can get one of those at every node of the branch and bound tree. So in terms of run times, this is a lot faster now. So as a comparison with what I said before, it's a speed up of 15 times for two hidden layers of 25 neurons, and it goes as far as 39 times when you have two hidden layers of 100 neurons each. All right, so that's solving the optimization problem, but you might be wondering, how can we make these neural networks smaller with that? Now, there's a quick recap of linear algebra for you. So let's say, what happens when you have a neuron that's stably inactive? Okay, we look at this neuron. This neuron is always producing a zero no matter what we try to do, so we can just remove it from the neural network. Well, we can also have the entire layer being stably inactive. And if that happens, that means that this layer is always producing a vector of zeros, which means that no matter what input is sent through the neural network, your output is always going to be the same. So basically, you're modeling a constant function. You can throw away all your hidden layers, but in fact, you can throw away the entire neural network, because this is a very bad neural network. So I wouldn't expect this to happen in practice. Now, we can also have the entire layer being stably active. That's something that we can observe, especially after we remove stably inactive neurons. In that case, we don't have a nonlinearity between inputs and outputs. So basically, the output is an affine transformation of the input, which means that when we look at the pre-activation output of every neuron in the following layer, we can reshape it to be an affine function of the inputs coming 2 layers before. Which basically means that we can rewire the neural network and throw away this stably active layer, as long as we change the weights and biases connecting the layer before with the layer after. Now, we may also have a situation where some neurons are stably active, not all of them in the layer. Now, in a case like that, we have a local linearity here. And if it happens that the rank of the submatrix of those weights is smaller than the number of neurons involved, we know that there's some linear dependency between the outputs of these neurons, and we can potentially, by changing the parameters of the affine transformations using them, remove at least one of them, for example. We can just remove, we can get rid of the rank deficiency by doing that. Now, then the final question is, are we going to find stable neurons? The answer here is perhaps. It really depends on how you train the neural network. So there was a prior work by Cheng, Chow, and Tedrake, where they were using MIP to do verification in neural networks. And they realized that this problem becomes easier to solve if you use L1 regularization. Now, the role of L1 regularization here is that this is going to help us push the weights of the value of the weights down more than with L2 regularization, for example. And then if, for example, if you have a bias which is negative and you're pushing down your weights, you're more likely to get a stably inactive neuron. Now, if you're pushing down your weights and you have a bias that's positive and it's going to be larger comparatively, it's more likely that you're going to get a stably active neuron. And if you add some, but not too much regularization when you're training your neural network, you actually can get better accuracy. So here's some results on MNIST classifiers. Let's say here that we choose, so what we did here is we chose an amount of regularization that actually provides us the same accuracy as not using regularization, just to see what would happen. And we also tested half that amount of regularization because it's a situation where we actually get some improvement in accuracy, and potentially we can also compress the neural network. So here we have some results for hidden layers of width 100. We have from 2 to 5 of those. And what we can see here is that if we don't apply regularization, we don't have compression. If we apply a lot of regularization, we get about 25% of the neurons removed. In terms of the connections, that's about 40%. But right in the middle here, we have the sweet spot. These are networks that are better, have better accuracy than the extremes, and they're compressible. We can remove about 15% of the neurons in them. And if you're curious about accuracies, you can see them in a lower font here. Now, we also tested this with 2 hidden layers, but increasing the width of the layers, doubling every time. We see a similar pattern going on here in terms of accuracy and the amount of compression we can get. Now, in terms of run times, we see that like this sweet spot where you can have the cake and eat it too is actually going to be a very expensive cake. You can set the run times right in the middle here are going to be a lot more expensive than in both extremes. There's some transition here to like a harder phase. It's sometimes, depending on the regularization that you choose, even for smaller neural networks, it's probably going to become very hard. And we observe the same thing when we have just 2 hidden layers, but we keep doubling the width of them. And there are some timeouts here whenever we reach 2 hours. Now, what we observed here is that this column in the middle is the harder case. Like it's where like it takes longer to do these things. When we have more regularization, it's the easier case. So it's a curve that goes up and down. And finally, here's something very interesting that we found out as we were analyzing compression and our L1 regularization, which is that from the moment you put any amount of L1 regularization in your neural network, the accuracy of the neural network is going to be linearly proportional to the, at least for like reasonable choices of regularization, it's going to be proportional to the size of the compressed neural network. So you're going to be able to compress more than neural network if the neural network is not so accurate. And you can see that like when you look at the balls that don't have like any filling, those are the cases where we don't have regularization. They're outliers of this curve, of this line here. And this is like a regression with an R-square of 64%. Now we also have some tests with MNIST autoencoders. So the idea of the MNIST autoencoder is that you're going to try to produce an output equivalent to the input. And in that case, if we do add a lot of regularization, actually we can fold the first 2 hidden layers of the neural network. We can pretty much like collapse the neural network considerably. And the patterns are as before, but by just adding a lot more regularization here, you observe that the loss doubled or even not that much. And whereas the amount of compression was considerable, we were able to remove between 5 and 10% of, we were able to find neural networks that were 5 or 10% the size of the original ones. In terms of run times, that's where it gets even more interesting. As we're adding a lot more of regularization, we have this smaller structure emerging, and obtaining it is very fast. So it's the easiest optimization problem to solve. Now, in conclusion here, we presented the general purpose exact compression method, which scales to networks large enough for practical use. Now we're talking about 1,000 neurons approximately, and more than 2 hidden layers. Runs faster than training the network, at least in CPUs. If you're talking about GPUs, that's a different matter. In a nutshell, what we did was we were removing and merging neurons, folding layers, and even collapsing the entire network in some cases. When these neural networks were trained with L1 regularization, any amount of it. And we were doing that because the stable neurons induce a linear behavior on the neural network. And the way that we were doing that is by solving an optimization problem, because when you need it, MIP is there for you. So if you'd like to bring on some questions, I think that's the right time now. Thank you very much.
Great, thanks, Thiago. Very nice. Let's just take one question here. So Wei Jun is asking, did you do cross-validation, and what was CV accuracy for this?
Oh, if I did cross-validation, so all the accuracies that are presented here are on the test set. They're not in the training set anymore. Does that answer the question?
Probably, yeah. Let's do one more. Can we say anything about the impact of dropout during training on the compressibility of the network?
Okay, that's interesting. I don't know. I know that dropout affects a little bit the type of neural networks you can obtain. They might have fewer linear regions. That's one thing that I have been studying other papers. So I can imagine they might compress things a little bit. That's a very good point. Thank you very much for the question.
Okay. There's another question here, but I'll send it to Slack, and we'll move on to the next talk. Thank you very much.
All right. So if you want to take a quick print, here is the papers that that might be relevant if you want to learn more about this. And just as a short observation, I just started looking at these things because I realized that neural networks are disjunctive programs. And I was only able to see that because I spent a lot of time thinking about disjunctive programming with Egon. So I would like to posthumously thank Egon for bringing me in this direction.